Welcome to our lecture online, and here's a really interesting problem, one that I personally was always very interested in, is what is the tension on the cables that are holding these gondolas that are being pulled up the mountain with the people inside. Let's say that the total weight of the gondola is 25,000 newtons, which is roughly about 2,500 kilograms. So it's the weight of the car plus some people inside the car. And the vast majority of the weight is being held up by this big cable that holds this gondola is being pulled up. The blue cable is the one that actually makes gondola move, but the predominant amount of weight is carried by this big black cable right there. And so since there's a bend in the cable, the angle is steeper on the front end here than on the back end because of the weight of the cable. And if the angle here is 4 degrees relative to the horizontal and 35 degrees relative to the horizontal there, what is the tension on this side of the cable? What is the tension on this side of the cable? Because it's not the same. And then the difference of that will of course be carried by the cable that actually pulls the gondola up. And we make the assumption that the gondola is being pulled up at a constant speed, so there's no acceleration involved. How do we calculate the tensions on the black cable? So we're going to do that first. We're going to be ignoring, well actually, we'll take that part off. Let's just go, we'll see what that ends up being in the beginning. We're just going to find out what T1 and T2 is equal to, and then finally, for part B, we're going to find out what the force is required to pull the gondola upward. All right. So how do we figure that out? Again, since everything is at equilibrium, and so you say, well, wait a minute, the gondola is moving, so how can things be in equilibrium? Well, if there's no acceleration, then there's no net force. So it's exactly the same situation as if nothing was moving at all. So if the gondola was just sitting there and not moving, or the gondola is being pulled up at a constant speed, it's pretty well the same as far as we can say that everything is at equilibrium. The only difference is that part of the weight will not be carried by this cable except by that cable as well, because it's being pulled up by the blue cable. So we'll start out by ignoring the blue cable and just working with the black cable alone. All right, if we do that, we get the following result. The sum of the forces in the x direction should add up to 0, and the sum of the forces in the y direction add up to 0. All right, so in order to do that, we need to find the x and y components of both tensions. So that means we need to find the x components. I'll just go ahead and put it right here. So this is T2 in the x direction, and here we have T2 in the y direction. So this would be equal to T2 times, and since this is the angle right here, that would be the adjacent side. So here we use the cosine of 35 degrees. And here T2 in the y direction would be T2 times the sine of 35 degrees. All right, we do the same over here. So we have the horizontal component, we have the vertical component. So we have T2 in the x direction, which is equal to, now notice if this is a 45-degree angle, and if we continue with the cable this way, then this would be the 40-degree angle there as well, which means in this case that would be T2 times the cosine of 40 degrees. And here this would be, I'm dealing with T1, am I not? We should call this T1, not T2, T1. And so this would be equal to T1 in the y direction. So it would be T1 times the sine of 40 degrees. All right, now with a calculator, we'll figure out what that is equal to. So 35 degrees, the cosine of 35 is 0.8192. So this can be written as 0.819, getting ahead of myself, 8192 times T2. The sine of 35 degrees, 35, take the sine of that. That would be equal to 0.5736 times T2. Over here, the sine of 40 degrees, 40, take the sine. That would be 0.6428 times T1. And over here, this would be equal to, the cosine of 40 degrees is 0.7660 times T1. All right, so that's T1x. So now we have both x and y components of the black cable. We still have the weight of the gondola, which would be a y component. That would be 25,000 newtons. So I would go ahead and write that down here. So that would be the weight of the gondola, 25,000 newtons. And at this moment, we're going to ignore T3. All right, so what do we get? Sum of the forces in the x direction. Let's start over here. Sum of the forces in the x direction add up to 0. That is equal to, we have this positive force right here, so that would be 0.8192 T2. So that's a force to the right. What else do we have here? We have this force right here, which is to the left, so it would be minus 0.7660 T1, and those are the only two x component forces on the whole diagram here. So that will suffice. That means we can go ahead and solve for one of the two t's in terms of the other one. So let's say here we want to know what T1 is equal to, so let's move that across. So we have 0.7660 T1 is equal to 0.8192 T2, and divide both sides by 0.766. We have T1 is equal to, so take the inverse of that, times 0.8192 equals, so T1 is 1.0694 times T2. I say, wait a minute, that can't be possible. The tension in that cable has to be the same on both sides, and yes, in actuality, it has to be. Because what's going to happen is the difference of the tension will be taken up by the tension in cable T3. And so therefore, that will work itself out, so don't worry about it. But right now, if it wasn't for the fact that this cable is pulling the cable car up, this tension would have to be greater than that tension. So we'll see in just a moment how that works out. Sum of the forces in the y direction. Sum of the forces in the y direction is equal to 0. And so let's count all the forces in the y direction. We have the upward force right here, which is this force here. That's a positive force, 0.6428 T1. Then we have the negative force right here, which is minus 0.5736 T2. And then we have this negative force, minus 25,000 newtons. All right, so what we're going to do here is we're going to plug in T1 for this equation right here in terms of T2, and then solve for T2. So we can say that 0 is equal to 0.6428, and instead of writing T1, we're going to write 1.0694 T2 minus 0.5736 T2 minus 25,000 newtons. All right, we'll solve that equation for T2 and see what we get. Let's see here. Multiply these two together. We get 0.6, we got that, so times 0.6428 equals, and subtract from that minus 0.5736 equals, so, and we move that across, we get 25,000 newtons is equal to 0.1138 T2, so therefore T2 is equal to, take the inverse of that, times 25,000 equals, so we get 219,677 newtons. 677 newtons. Okay, now notice I have way more significant figures than I need, but I'll just keep that because I'm still calculating things. Later on, we will round them to the proper number of significant figures. All right, so now we have a value for T2. And plugging that back in here, we can figure out a value for T1. So T1 is equal to, so take that number, multiply times 1.0694 times 1.0694, 1.0694 equals, and we get 234,922 newtons. All right, so there are the two tensions on the cable, which means that the tension on this side would be 234,900 newtons. The tension on this side is 219,700 newtons. Now, what's really interesting to note here is the cable car itself only weighs 25,000 newtons, yet the tension on the cables holding up the weight is almost 10 times as much. Imagine how big those cables need to be in order to be able to uphold the weight of that. Now again, what we can say is that the difference between those two should not exist. The tension should be the same on both sides, but the reason why T1 appears to be bigger than T2 is because actually the difference is taken up by the tension in cable T3. So what we can say is that T3 should be equal to the difference between those two, which is therefore 234,922 newtons minus 219,677 newtons. And let's see what that is equal to. So 234,922 minus 219,677, and we get a difference of 15,245 newtons. All right, so now that we've figured out what the tension is on T3, the actual tension on T1 has to be equal to what we had here before minus this value right here. So let's go ahead and then find the true value for T1. So T1 true value is going to be equal to that, which is 234,922 newtons minus the tension carried by T3, which is 15,245 newtons, which of course is going to give you the same value as we have for T2, which is 219,677 newtons. All right. So that is then the answer to our problem. So now we have the initial values that we had without taking T3 into account, but if we add T3 into account, we then can see that the tension on cable 1, tension on cable 2 has to be the same. It's the same cable. You have to have the same tension, and the difference is therefore carried by T3. And that's the answer to our problem.